So, good evening, everyone. Welcome to the third edition of the Radio Astronomy Techniques seminars. We are very lucky today to have Dr. Francesco de Gasperin as our speaker. Let me provide a brief introduction. Francesco de Gasperin did his PhD in astrophysics in 2012 from the Max Planck Institute in Germany on the impact of radio-emitting supermassive black holes on their environments, the LOFAR view of the Virgo cluster. Following which, he was a research associate at the University of Hamburg, after which he joined as a Venn Fellow at the Leiden University in the Netherlands, following which he held a position of junior professor of radio astronomy at the University of Hamburg, Germany. And after which, since 2022, he's a staff scientist at the Institute of Radio Astronomy in Bologna in Italy. It is my pleasure to welcome him at this seminar, and we are eager to learn about the low frequency, ultra low frequency studies that he is going to tell us about. To mention many of his accolades, he has been awarded the Young Scientist Award of the International Union of Radio Sciences. And he has received an ERC Consolidator grant for ultra-low frequency studies from the European Commission in 2023. So welcome, Francesco de Gasperin, and we are eager to hear about the recent LOFAR innovations in ultra-low frequency astronomy.
Thanks, Rota. Thanks, Rota. I share my screen and go full screen. Okay.
Yes.
I think you should see everything now.
Yes.
Okay. So in the next hour or so, I will try to dive you a bit into the low frequency universe. So what is the best instrument that we have at the moment? Yeah, this image is a bit of a spoiler because to work at the extremely low frequencies, now LOFAR is the instrument to go, but it's not the only one. I will mention this later. I also would like to discuss a bit what are the challenges to observe at these frequencies and why we want to do that. Then I will also explore a bit the plans that we have for the, let's say, coming decade. So short to mid-term plans for the low frequency world. Okay. So this was an image that, as Ruta mentioned, I made when I was in Munich during my PhD. This was 2012. This is M87 Virgo A for radio astronomers. And it's not that impressive. We have better images, but this image was taken at 100 megahertz, around 100 megahertz, and was one of the first images that we managed to obtain with LOFAR. It was a lot of work. And very recently, we made another image of M87, which is this one. The point here is that not much changed in terms of telescope. So the antennas were kind of the same. We added more data, but we could add them also in the past. The point is that in 2012, we really didn't know how to do most of the data reduction at these extremely low frequencies. But now we developed a lot of know-how and a lot of techniques, a lot of software as well has been written, so that we now can take the data, even the data of 2012, and obtain images that are much, much better. So in this image, in this case, we reach a 2-3 arc-second resolution, which means that we are also using the VLBI part of LOFAR, and with the core part reaches a 0.3 arc-second resolution. This image is at 150 megahertz, by the way. So this is an extremely high resolution than with indeed the LOFAR VLBI. That is a technique that we learned how to use it only in the past few years. So in the rest of the talk, I would like to explain, first of all, what is LOFAR? Just a very quick introduction, because I guess most of you have an idea. And I will focus mostly on the low band antennas. So this is the low frequency, the very, very low frequency system of LOFAR. So working below 100 megahertz. That's my interpretation of ultra low frequencies. I guess many of you are familiar with GMRT. GMRT is a low frequency telescope. Actually, we have to use a bit, sometimes we have to invent some new words, because usually below 1 gigahertz is usually called the low frequency. So I try to use ultra low frequency for anything that is below the 100 megahertz. I will then discuss a bit the techniques that we are using to calibrate LOFAR LBA data and the pipeline for LOFAR LBA, which is called PIL, which is this pipeline that we developed. I will then introduce a bit the LOFAR LBA Sky Survey, which is something that you can actually directly experience and use for your research, so it might be even directly useful for you. And then I will outline what we plan to do in the future. This is the usual LOFAR image. In the background, you see the super TERP, it's the superstation that we have at the center of LOFAR. And here you see the distribution of stations of LOFAR across Europe. We have around 50 stations. Most of them are in the Netherlands, and about 15 are spread in other countries, 6 in Germany and so on. We have one in Italy and one in Bulgaria that will be built in the next year. So the telescope is still expanding even after 10 years. And when you use all the international stations, this is typically called the LOFAR VLBI mode. So when you have these very long baselines. We have, as you can see from the image, we have 2 types of dipoles on the ground. We have these square panels here that each of them contains 16 dipoles that are the high band antennas. They work about 150 megahertz, at about 150 megahertz. And then we have these kind of sparse distribution of dipoles that are the low band antennas. So these are larger dipoles, about 96, well, exactly 96 per group. And here in the superstation, you have 6 groups, and then you have 96 dipoles in each other stations in the Netherlands and abroad. And the high band antenna works at 150 megahertz, as I told you, and the low band antennas, they work from 80 megahertz down to the ionosphere cutoff frequency of 10 megahertz. So that's the lowest frequency that you can actually achieve from ground observations, because below that frequency, the ionosphere becomes opaque. You have to go in space to do radio observations. Obviously, the closer you get to the ionosphere, we will see later, the more difficult it becomes to avoid the systematic effects that the ionosphere creates. So there are several challenges in using low-frequency telescopes. You probably are well aware about this. With LOFAR, we have definitely a major issue when we have to work with our data because of the data size. We can collect up to several terabytes of data per night. Then the data are kind of in real time or quasi real time averaged down, but we still already collected several tens of petabytes of data in these 10 years. And this is obviously a challenging for archiving, for retrieving the data, for downloading. So this is a whole scaling up of what we were used to do with BLA and more like previous generation telescopes that you can reduce the data on your laptop. And now this is definitely not feasible anymore. The LOFAR has dipoles, doesn't have dishes. So this usually, and this is the case, implies that it has a complex beam shape, very hard to derive and to implement as a model. So this is a problem that I'll show you later some of the consequences. It also has a very large field of view. Here we are working at very low frequencies, and the field of view can be up to like several degrees in the sky, which means that the sky you are imaging is very large, very complex, and therefore every type of error that is direction dependent will bite you very, very strongly. And again, we will clearly see that later. And we have a low signal to noise. And low frequencies, the sky is very bright, and the T sky is the temperature of the sky is extremely high, and this will very much limit the signal to noise that you have at your disposal. And finally, we have the ionosphere, which is our main systematics, and one of the sources of my nightmares for the past 10 years. So here is a bit the differences between HBA and LBA. So these are just a list of numbers. We don't have to go through them, but you can have them as a reference. Very quickly, frequency range, I told you, this is the frequency ranges we are covering with the two systems. The typical sensitivity with a few hours of observations is about 1 millijansky beam in LBA, 50 megahertz, and about 0.1, so 100 microjansky beam in HBA, 150 megahertz. And this 1 millijansky beam is anyway a very good number. 50 megahertz is about 100 times deeper than competitors. The resolution, when you use only the Dutch array, which is much simpler because the baselines are shorter, you arrive to about 15 arcsecond in LBA, 5 arcsecond in HBA, but you can reach the 1 arcsecond when you use the VLBI LOFAR in LBA, and 0.3 arcsecond in HBA. So the primary beam, as I told you, is several degrees in full width of maximum. And typically we have 96 megahertz bandwidth that we can use in one single beam. And finally, and very important, mostly in LBA, we have fully multi-beam capabilities. Multi-beam capabilities means that we can observe in multiple directions in the sky at the same time, which is extremely cool because it opens up a number of new observing techniques that in the past were not really doable because we were forced to look just in one direction in the sky at the same time. For example, the whole concept of cross-calibration, moving back and forth from a calibrator, this is not useful anymore with LOFAR, because with LOFAR you can just put one beam on the target, one beam on the calibrator, and observe them at the same time. So obviously one has to change a bit the mindset in the way they do the data reduction and also the planning of the observations. So let's discuss a bit the beam of LOFAR. So this is the distribution of dipoles, of LBA dipoles in a station. You see they are kind of randomly distributed. This is to minimize the side lobes when you phase up the signal of all the dipoles. And this is just a very quick idea of a sketch of what it can be. The beam of a single dipole is obviously a fixed beam, which is maximum at the zenith, and it goes down at low elevation. This is not movable because the dipole are fixed on the ground, which means that if you observe a low elevation, you intrinsically have less signal coming to you. So that's why LOFAR is much better at observing at higher elevation and therefore at higher declination compared to other telescopes. For example, GMRT doesn't care too much because it just points the dishes, but we cannot point the dipoles. So we are forced to stay at high elevation. If we go at low elevation, then immediately the shape of the dipole beam will bite us and reduce the signal that we can obtain. And that's why we hardly go below the declination 0 with LOFAR, although in theory we can observe down to -10, -15. Then one can create a station beam. And how can you do that? You simply add up the signal coming from all the dipoles, and you add them up like in phase. So you simply sum the signal coming from all the dipoles without applying any delay to anything. And obviously you are in this way, you are maximizing the signal that is coming right above from you, but you are at the same time killing all the signal coming from other directions, because these other signals will hit all the dipoles at different time. And if the signal is added up all without any delay, then you are decreasing the signal. In this way, you are really focusing the beam of your station right above you. And in this way, you indeed reach a beam of a few degrees. Clearly, this beam is steerable. You can point it in multiple directions, simply up. This is with no delay applied, but you can apply a certain delay across your dipoles, and applying this delay, you will maximize at this point the signal coming from a certain specific direction that you choose. And in this way, you are kind of really pointing the stations in different directions. And this is the way we point the telescope. Obviously, you have to include the dipole beam. So if you point too low in elevation, as I told you, this the signal will be lowered. But nothing prevents you from collecting the signal, applying different delays, and look at the sky in two or even multiple directions at the same time. And this is the multi-beam capabilities of LOFAR. So at the moment, we don't have enough hardware at the station level to use all the dipoles at the same time, but we can use only half of them in LBA. So you can choose whether to use, there are three modes that you can use. There is the inner mode, use only the inner half of the dipoles, or sparse mode, use like randomly selected dipoles across the station, or you just use all the outer dipoles of the stations. Clearly, this creates a different station beam. This is going to be larger with the inner, because it is effectively you are creating a smaller dish, let's say, which is up to 10 degrees, but there is a mutual coupling and crosstalks between the dipoles, so this mode is usually not used. In the past, we most of the time use the outer mode. This creates a field of view of about 4 degrees full width at maximum, but being a kind of a donut-shaped dish, it obviously creates some weird patterns in terms of side lobes. So we now moved to use sparse, which actually simply decrease the sensitivity of the entire station compared to use all the dipoles, but at the same time create a nice side lobe patterns and a full width that is about 6 degrees, so still manageable. So there are different modes that we use to observe with LOFAR. There are some typical modes that has been implemented during the years to observe with LOFAR LBA. And I want just to show you these modes because it can explain how you can exploit these multi-beam capabilities. This also will be very relevant for SKA law, for example, because SKA law will be able to do the same. So, for example, we have a survey mode where we took our all the bandwidth that we have available, because we are limited by the amount of bandwidth, because of the amount of data we can send to the correlator. And we divided it into 4 beams. We put 1 beam on the calibrator, and 3 beam, we put them on our target fields. And we then cycle various targets in the sky, so to cover large area. This is how we do surveys in LBA. And it turned out to be very effective. We always have a beam on the calibrator to study the stability of the telescope and to transfer solutions. And but we also maximize the survey speed with the other 3 beams. If we have a single target, for example, a deep field that you're very interested in, you can increase the bandwidth, so you can go a bit deeper, a bit faster. So increase the local survey speed on the deep field. You put 48 megahertz on the calibrator, 48 megahertz on your whatever deep field you want to do, and you observe for many, many hours. So that's another observing mode that has been widely used. We also implemented co-observing mode with the surveys. For example, you can apply for time, at least in the past, because now LOFAR is not opening, doesn't have open time anymore because we are upgrading the telescope. I'll talk to you about this later. You could use one of the survey beam to point whenever you want. In the meanwhile, we were doing the surveys, and this was kind of a win-win situation because we can get some telescope time, but at the same time, we will reduce the data for you. I think this is was a very smart approach to simplify the life for users, also get the data very quickly for the telescope, and I hope that also with the SKA law, there will be ideas like this implemented where multiple observations can be carried out at the same time, joining the efforts. In general, there were no international stations used in LBA, but at the moment we are doing some experiments on them with reasonably decent results. Doing VLBI at 50 megahertz is extremely challenging, so that's why we didn't do it in the past. We usually have an hard cutoff in elevation at 30 degrees. So the survey we did, for example, was cut at 20 declination, so only above 20 declination. This was indeed to minimize the complexity of these observations. And we usually do multiple short observations of 1 hour. And this is kind of a lucky imaging approach because we just continuously cycle on our targets, changing them every hour, so that if 1 hour is bad because the ionosphere was very bad, then we can still use all the other hours, for example, taken in different days or even different weeks or months in the past or in the future. Obviously, you are not limited by the number of beams. You can even split your bandwidth into a very, very large number of beams and observe, for example, 30 sources in the sky at the same time. And this is what we did for this 3C survey. We did the survey of all the 3C objects. These are like about 200 objects in the sky. So we wanted to observe them for 8 hours each. So we pointed 30 beams in the sky at 30 different 3C sources, and every hours we were just changing the beams to try to just observe the 3C sources that were up in the sky. And this is how we collected the different the data on all the 3C sources in chunks of 1 hour. And you see at the end all the 3C sources collected 8 hours of observing time. But this was really cool because we could observe 170 plus sources in just 6 runs of 8 hours each. So it was very, very, very good. So why we want to go at these ultra low frequencies? I mean, this is now a very brief overview on the science that we do at ultra low frequencies, and is mostly focused on my preferred topics, which is the study of the large scale emission, so on galaxy clusters and beyond. Typically at high frequency, you have high energetic phenomena that accelerate electrons, and these electrons, they emit high energies, so they create usually rather flat spectrum sources. But obviously there is also low energetic phenomena happening in clusters, but everywhere. And these phenomena are only able to accelerate low energy electrons, therefore creating rather steep spectrum sources that you can only detect at low frequencies. And we have a number of these type of sources that became visible in the past years, also thanks to LOFAR. And related with the study of the large scale structure. This is a picture that shows you, this is just a simulated X-ray image of the large scale structure. You see there are galaxy clusters here, there are smaller clusters, there are filaments. And these are the sources that we can detect when we observe at, let's say, gigahertz frequencies. We have radio galaxies, probably bent because of the interaction with the intercluster medium. We have radio halos, we have radio relics, all well within the central region of the galaxy cluster. But what happens if you go at ultra low frequencies? When you go to ultra low frequencies, there is a plethora of other phenomena that becomes very much visible. We have ultra steep spectrum radio halos showing popping up in like less massive clusters. We have very long tail, maybe gently re-energized by the interaction with the intercluster medium. We have radio phoenixes. We have radio bridges that were recently discovered with LOFAR connecting pre-mergers galaxy clusters. We have radio mega halos also discovered recently with LOFAR that engulf the entire galaxy cluster out to R500 and even more. And all these things are very inefficient phenomena that can only be observed when you go at very low frequencies. A very good example was the gently re-energized radio tail. This was an observation of a galaxy cluster called 1033. And you see that with the VLA observation, we couldn't see anything. There was this nice wide-angle tail radio galaxy, but we observed the same object with LOFAR, and suddenly all these elongated tail appeared. We did a spectral analysis using indeed a GMRT at 300 megahertz and LOFAR at 150 megahertz, and this emission was barely detectable in GMRT. We could derive a spectral index of -4. So the spectral index of that part of the source is extremely steep at the level that if you extrapolate that through VLA regimes, it might take up to 100 years to detect that emission, 100 years of observing time to detect that emission. Obviously, the spectral energy distribution, then we, with other observation at 50 megahertz, we discovered is curved, so it doesn't maintain the -4 spectral index forever, but is expected indeed to be curved. And this is probably a very gentle re-energization that slightly and that perfectly counterbalance the losses along the tail of the radio galaxy. Also, ultra-low frequencies are very good to detect aged plasma. This is the typical flux density frequency plot. This is spectral energy distribution of a radio source. After 10 mega years, there is this cutoff that develops, and this cutoff move towards lower and lower frequencies with time. And obviously, if you observe in this frequency range, you can detect this very, very old plasma. And this is the same image of a galaxy, of a radio galaxy at gigahertz frequencies and at megahertz frequencies. And you see that the very, very long tail is only visible at megahertz, where you see all this aged plasma. Also, low frequencies are very good in constraining models. For example, this is from the hotspots of Cygnus A, where different models can explain the turnover, but only with points at ultra low frequency, you can really disentangle different models. Okay. Another important thing that you can do at ultra-low frequencies is that ultra-low frequency interferometers at ultra-low frequencies are very good at detecting extended emission, because baseline is measured in wavelength. So we can, for example, use the most famous supermassive black hole of the universe, which is the one at the center of M87. And you see that this is what you see at 230 megahertz. If you go to lower frequency, you start being sensitive to larger scale. You see the jet. Then you go lower frequency again, at gigahertz frequency, you see the entire cocoon. If you go at 50 megahertz, so lower frequencies, then you start appreciating the entire long-term interaction of the supermassive black hole with the surrounding environment. And this is really something that the supermassive black hole needed hundreds of mega years to create, and is on very large scales. And therefore, for these two reasons, you can really appreciate this only observing at low frequencies. So this was just a series of reasons why low frequencies observations are interesting. And now I want to move a bit on the technical side. So what are some challenges that we have when we observe at the low frequencies? One of the typical challenges, as I told you before, is the beam shape. We have a complex beam because it's made by all these dipoles spaced up. It's extremely direction dependent because indeed the dipoles projected in the sky, the dipoles distribution is changing in every direction. So we have a model for that kind of explain some of the things some of the systematics that the beam creates on the LOFAR data, but not all of them. And these are, for example, some of the leftovers that we have on the LOFAR bandpass. This is the LOFAR bandpass as derived with our calibration software. And here you see you should have a very smooth and nice bandpass, but you have this kink at about 60 megahertz. And if you observe in another direction in the sky, the same kink is now in the other polarization. And this is just to underline that this is a very direction-dependent effect that, depending on which position in the sky you are looking at, can move from one polarization to another. And is also visible in these images. I will show several of these. These are solutions after calibrations. This is time, this is frequency, and color-coded here you have amplitude solutions. Here you see clearly the bandpass. This is rather stable in time. There are all these quick vertical lines. These are all scintillations because of the ionosphere. But once you remove the bandpass, you see that there are here on top some stripes that are exactly these kinks. These are leftovers from the beam model, the element beam model that we were not able to model properly. And this will be a challenging also for SKA, and I really hope that we will be able to have a very good model for the beam for SKA, because this makes your life extremely easier when you have a good beam model. Another problem is that we don't have a dish again, therefore we have rather weird side lobes, usually rather high. Therefore, if you observe in whatever direction, you almost always have one of the very bright A-team sources. The A-team sources are, for example, Cygnus A, Cassiopeia A. These are the two brightest, but also Virgo, Taurus can be problematic. That actually spill some of their flux, which I remind you at 50 megahertz is 10,000 Jansky or so it's extremely bright. These sources are extremely bright, and even like a few percent entering in one of the side lobe can completely wash out your image with artifacts. So we had to figure out some strategies. We have a strategy in place that is called the mix, that is a kind of a peeling strategy. So you try to calibrate that source and subtract it from the data. Is working, not always. When the source is too close, it becomes very complex. But this is something that we will have to face also for SKA. Also, as I told you, the primary beam is non-negligible. This is a nice image that you can see all the flux in the well within the full width of maximum. Then you have the first null of the primary beam, and then you see all these sources. These sources are in the first side lobe, so they are like 10 degrees outside the face center, but still they contribute maybe 20, 30 Jansky on the total flux in your images. So this is a lot of Janskys for things that you usually ignore. And so we actually cannot ignore sources in the first side lobe, mostly when we work with LBA outer, so using this donut shape distribution of dipoles. So actually we had to, with sparse, we are doing a bit better than that. So this is the first null. And obviously the low sensitivity. So here is the source equivalent flux density. We have the minimum at 54 megahertz. That's why all the most of the LBA observations are centered at 54 megahertz. And we are mostly dominated by T-sky. So the sky is extremely bright at those frequencies, and it's very hard to overcome this limitation. Clearly, we have the ionosphere. The ionosphere is continually changing above you. It creates a lot of artifacts, typically all this starry shape around, starry artifacts around your sources. These are phase error induced by the ionosphere that really moves your sources continuously in the sky, and you this invalidate one of the basic assumptions of interferometric, that the sky is the same for the entire aperture synthesis. And here I would like to show you why this is a problem at low frequencies, mostly a problem at low frequencies. This is the phase effect induced by the ionosphere, where you have a refractive index along a certain line of sight. And this is the integral divided by C is the delay that is imprinted by the incoming radio waves. Multiplied by nu, you have the phase effect. You can expand this refractive index, is Taylor expansion. So we just get rid of everything that is not interesting here. And we see that the refractive index is actually goes with the a certain factor divided by nu square. Here you have a nu, so the phase goes at the first order with 1 over nu. And this Ne is the electron density in the ionosphere. So this is telling you that the phase effect on your incoming waves, which is what you care when you do interferometry, goes with 1 over nu. So the lowest frequency is the worst is this effect due to this expansion of the refractive index. And this effect is proportional to the amount of free electrons that you have in front of you. Clearly, you don't care too much about the total electrons as long as this is the same across your entire array, but typically this is different from different antennas, and actually is different from the different direction across your image, so it makes a lot of problems. Also, you have second order effects that many times you neglect, but when you work at 50 megahertz, you cannot neglect. These are second order effects. This is the Faraday rotation. This is 1 over nu square, because again of this nu here. So the phase goes with 1 over nu square, and is proportional to the amount of free electrons and the magnetic field. So this is a bit even more difficult to model because you need also model the magnetic fields. When you go below 40 megahertz, you even have third order effects, which are usually totally neglected, but actually we can definitely see them when we do observation at 30 or 40 megahertz. This term here is actually dominant above this one here, and it goes with the total the amount of free electrons that we usually measure in total electron content. And this is a ionospheric scientist way to measure how many free electrons you have in the ionosphere, which is actually telling you this number here. So it goes with the total electron content squared, which means that it depends on the stratifications of the ionosphere. So, this is the reason why going to lower and lower frequency becomes more and more challenging to deal with the ionosphere, because these terms become less and less negligible. And yeah, these are all the frequency dependency I told you. So let's see what they look like. So these are images that show you for a 6-hour observation, you have time on the x-axis, and here on the y-axis in the first plot, you have the total electron content. And actually, we were really able to derive the total electron content simply looking at the phase errors that were imprinted in our data. So here we look at the calibrator, we solve for the phases, and we derive the 1 over nu effect across our band, and see how it changes. The colors here are the different stations, the different LOFAR stations, and you see that all these waves. These are the different total electron content changing above the different LOFAR stations. And obviously this creates a differential phase, and you really need to solve for this. This is a very strong differential phase. But you see that for some stations, there are some correlations. And this is because these stations are probably nearby, and this everything is a reference to the core, so to the center of the Dutch array. And the red stations are both like in the same locations, so they kind of trace each other because the same ionosphere is passing above them. And we can also derive the second order effect. This is the Faraday rotation. And even the third order effect is a bit more noisy because you see it only at low frequencies, but it's really clearly present. And you see that the three effects kind of also speak within each other, because the Ne, the number of free electrons, is actually present in all the three terms of the Taylor expansion I showed you before. Okay, let's see how we usually calibrate the low frequency data. And I would like also to show you how you can do it in practice, because maybe you are interested in testing it, or you want to test our pipeline on other data set taken with MWA or taken with GMRT. You're very free. The pipeline is freely available at this GitHub. There is a Docker that you can download. You can create your singularity with this command here. Everything is written in the slides, so you will have them. The idea is that you can stage the data online. We have a website. You can select which data you're interested in. Then the data are staged. You get an email with all the staged data. And then we have a pre-processed pipeline. This is the first pipeline. On the README of the GitHub, this is all explained very well. We have a pre-processed pipeline that automatically downloads the data and does some manipulations. I'll show you later. Then we have a calibrator pipeline working on the calibrator beam. I told you we always have a beam on the calibrator. And then we have a self-calibration pipeline, a direction-dependent pipeline, and extraction pipeline that work on the target. And they do a more and more refined job on imaging better and better the target. So the idea of these three pipelines of the target is that after the self-calibration pipeline, you corrected all the instrumental after the calibrator pipeline, you can transfer the solutions and you corrected all the instrumental errors, but you still have all the ionospheric errors imprinted in your solutions, in your data. So that's why you see all these artifacts. Then after the self-calibration, then you do a self-calibration, so you correct the direction independent errors across your entire field, and you have a second image. This is after the self-calibration pipeline. And here you see that you get rid of most of the ionosphere, but obviously you have all the direction-dependent errors still imprinted. And at 50 megahertz, these are extremely strong. So you still have a lot of errors everywhere. Then you have the direction-dependent pipeline that tries to derive the ionosphere in multiple directions, and then it cleans up the image much better. And you should achieve the 1 millijansky beam thermal noise. So the pre-process pipeline, so download the data, flag low elevation, because I told you low elevation data, so this is very low signal to noise, does some rescaling, try to remove, if this has not been done already by the observatory, tries to remove the A-team. This is an example observation without the demixing of Cassiopeia A, which is this source here. And after the demix of Cassiopeia A, this is the sausage cluster that is very close to Cassiopeia A, and is actually close also to Cygnus A. It's a very unlucky target. But you see before and after the demixing how much of improvement you have, and how useless is to try to calibrate your data without removing the A-team when you are, even here that we are at, I think, 15 degrees away. So it's not a couple of degrees away. So it's really far, but it's still a problem. Then it does some averaging and renaming, so not very important. Calibration pipeline. Calibrator pipeline works on the calibrator beam. We usually use only two calibrators, 3C196 and 3C380. These are the best calibrators we have. You can also use 3C295, but usually these two are always, one of the two is always up in the sky, but sometimes you have to use 295. The problem is that 295 has the turnover, and it's not that bright. Also, it's not that good because it's a double source. It's not get that good for the calibration of the international stations. 196 is by far the best calibrators you have. So if you can, use 196. We use one of these, typically one of these two calibrators. We solve for the cross delay between polarization, the Faraday rotation, the bandpass, and phases in the calibrator direction. Then we transfer everything that is instrumental, which is non-direction dependent. So to the target beam. Then we also have implemented some new strategies very recently. For example, we do a phase up over the core station. We solve only the core station, so the very central part of the array. We solve them, then we do a phase up. So the field of view become intrinsically much smaller. So you kind of smear all the other sources that are outside the center of the field of view, where is your calibrator. And then we solve for the remote stations, the international stations. And this approach turned out to be rather effective, mostly when you have international stations. So we implemented this. And so this is how it's currently done in the calibrator pipeline. And then these are some of this is the complex structure of the calibrator pipeline. And these are some of the residuals. I already discussed this, the amplitude residuals, and these are the phase residuals that, as you can see, are kind of uniform. So these are the phases at the beginning. These are the phases after the calibration. And you see that although we describe the entire LOFAR systematics as clock, tech, and higher order techs, Once you remove these three effects, you end up with very clean phases, which means that these few parameters, if you can derive them correctly, then you are able to really calibrate your data very well. The problem is to derive them correctly, because you can do it very well with the calibrator, but much harder is to do it on the target field. So the target pipeline, let's move to the self-calibration. The self-calibration, at the moment, we are implementing a bit of a smarter approach compared to the past. In the past, we were solving on the entire field. Now we are just solving on a smaller possible region of the field that contains a certain amount of Jansky. At the moment, we are using 40 Jansky. And this because you want enough signal that you can kind of phase up all your stations in that direction. But at the same time, you don't want to use your entire field because the direction dependence are already so strong that sometimes the most remote stations cannot really converge to one solution if you use the entire field. So this is a kind of an hybrid approach at the moment that we are using between a self-calibration and a direction-dependent calibration. This is our first step, and is at the moment replacing the usual self-calibration where you do a direction-independent calibration. At the moment, we are kind of doing this hybrid direction-dependent and direction-independent calibration. The difficult thing here is to remove the rest of the field. So you initially do a very quick and dirty direction-dependent calibration to remove the rest of the field and then focus on that larger region as a local calibrator to kind of phase all the stations in the same directions. And then you start doing all the normal direction-dependent approach. This is again very new, very developing. So we derived the tech with this self-calibration, the tech that is a general tech across the field of view, and the second order beam effect, which is again, we try to remove that. Then we have the direction-dependent pipeline. The direction-dependent pipeline is a bit more complicated. We have multiple approaches. We have at the moment, we are doing a serial calibration. Here we are actually taking advantage of finding the brightest calibrators around the field. And then we move on each calibrator once removing the rest of the field and calibrating in that direction, getting the solution in that directions. And this is a kind of a serial approach. It's very scalable and easy to implement. The alternative is to calibrate in multiple directions all at the same time. And obviously, this is a bit more complicated. You need more advanced software. There is KillMS and DPCube. Both can do that. And it's possibly faster and more precise, but it's a bit more difficult to, for example, put together sources directions that are brighter with directions that are less bright and so on. And then you have the imaging part. At the moment, we are doing facet imaging. In facet imaging mode, you have once you have solutions in enough direction, you need a software that is able to image each region of the sky, we're applying the solutions for that region of the sky. At the moment, there is both DD Facet and WSClean can do this thing. We are using WSClean at the moment. The other approach is to use screens. So this is a more advanced approach where you kind of interpolate multiple directions, and therefore you don't have any more the rough divisions between facets, but you apply your direction-dependent solution in a facet mode. At the moment, this is doable with WSClean and the IDG gridder, the image domain gridder, but it's still rather difficult, at least for us, to figuring out the right screen. So we are still working in facet mode. I'll go a bit fast here because it's already late. So I want to go actually showing some of the results of the survey. We are doing 3 surveys with LOFAR. There is LOTS at 150 megahertz, LOLS, the LOFAR LBA Sky Survey at 50 megahertz, and LODES that is at 20 megahertz. Now I will focus on LOLS, that's the survey I'm working on. There is a preliminary release that was available in 2021 and also first release done in 2022 of the EDDEX field, which is this region here. We already collected data for everything above declination 2024, again for this elevation cut. And we are now processing all these fields. It's a lot of data, so it will take some time where we plan to release at least all the extragalactic sky soon. These are some images taken from this first release. So this is the RATeS field. You see the images are reasonably good, corrected with direction-dependent calibration, and the noise is about 1.5 millijansky beam, so close to what we wanted to go. And this is the noise distribution. You see that there are a lot of regions where the noise goes up, which are the black spots. And these are because there you have bright sources. And bright sources still create some artifacts. Here you have 3C295, very bright, so creates a lot of artifacts around. But the distribution is still, apart from this tail of bright sources, is still quite good at about 1.5 millijansky beam. I wanted to also point you to this website where you can download the data. They are available. You can use them for your science. We have StoxI and StoxV. We have also a StoxV detection of a pulsar. So something was also visible in StoxV. Curiously, we didn't know that this was feasible. We have a catalog of 42,000 sources that you can also use. And you also can ask, but the data are not available online, to get the data if you want to reprocess some directions. And these are some images from extended sources that were used for publications. So what next? In the last couple of minutes, I just want to show you what we want to do with LOFAR 2. So LOFAR 2 is actually an upgrade of LOFAR that we are planning to do, that will improve the ability of LOFAR to mostly increasing the capability at the station level. So we will improve the hardware at the station level. With this improvement, we can now use twice the dipoles. So we will use all the LBA dipoles at the same time. So which means we have twice the sensitivity for all the LBA Dutch stations. And we can also observe LBA and HBA data at the same time. So the idea is that we can maybe use HBA to calibrate LBA even with the long baselines. So we do the LBI. We also have improvement on the clock distribution, the linearity for RFI, and other things. In general, this improvement will enable us to do a much better job in surveying the sky with LOFAR LBA. And that's why we are planning to do a new survey with a lot of, we ask for a lot of time, is several thousands of hours, about 6,000 hours of LOFAR observing time, to do a deep survey of the extragalactic sky and a bit of a shallower survey of the galactic and the low declination sky, to achieve about 300 microjansky beam of all the extragalactic sky. So this is the region we want to go. You see, pretty much in line with LOTS, and also pushing down to about 16 megahertz. And this is very interesting because this blue region here is where you have chances to start detecting emission from exoplanets due to the presence of their magnetosphere. And this is a very active research field, and we hope with this new survey to give an input to this field. Then we have a number of deep fields that we want to do even deeper, 100 or 500 hours, to achieve the 100 microjansky beam. For this, we really need to use LOFAR VLBI, otherwise we will be confusion limited. So it's a very challenging but very scientifically rewarding project. Yes, this is everything. Sorry, I have to rush a bit at the end, but I know it's a lot of information, and it's already 50 minutes that I'm talking. So if you want, you can ask me other questions of anything. Thank you very much.
Thank you, Francesco. Anyone having a question, please unmute and ask. I think we have the number of participants is not too large probably, so we can manage. Any first question, please go ahead and unmute. Okay, let me ask the first question. So very nice to learn about these new developments from the LOFAR LBA. So you showed the how you deal with the ionosphere. So I was wondering, with all the like a lot of direction dependent and self calibration, all these things basically, how do you keep the astrometric accuracy, or how do you verify it, the positions of the sources and so on?
Yeah, this is a well-known problem, has been also a well-known problem for HBA. There is always a cycle of alignment that you do afterwards. And this we are lucky because we like very soon there will be like more or less in like a few months there will be the data release 3 of LOTS, which covers most of the extragalactic sky. So we are like on the shoulder of giants because we can use LOTS to start our self-calibration, which is better than anything else available at the moment, and definitely better than what we can imagine with our initial self-calibration imaging. And also we can use LOTS to align everything. LOTS itself, I think, uses higher frequency, higher resolution surveys to correct for astrometric accuracy.
Yeah, thanks. There's one question from Hanumant in the chat. So he's asking what feeds are used for the low frequency observations.
What fields?
Feed the dipoles, I think.
Yeah, in this case, all these things I was discussing with the LOFAR LBA. So we are using LBA dipoles. LBA dipoles are extremely simple dipoles, just simple wires. And they work as a phased array. So this is a much cheaper version than what we will have with SKA. So it comes with problems as well. The coupling, the response is suboptimal compared to what we will have with SKA. At the same time, it was a very good compromise because we need 10,000 of them, so they need to be very cheap. So that was the compromise in deciding the dipoles.
Thank you. Dharam, please go ahead.
Hi, Francesco. Nice talk. Nice to see you. A quick question though. When the flux density uncertainty, is it still going to remain like 20% or 25%, or is there a scope to correct, like fix and make it more accurate further?
Yeah, that is very, very nice you ask, because I have a student now that is working on the 3C survey I mentioned before. And with the 3C survey, one very good thing that we can do is use the 3C sources to assess how good we are in transferring our bandpass and therefore our absolute flux scale to our target fields. Because the 3C are very well-known sources, so we have a very detailed spectrum with even points below the 50 megahertz. So we could check that. And actually, he showed that with the narrowband observation he's doing at 50 megahertz, he doesn't find any systematic error at the phase center because he's working on sources that are at the phase center. And he finds about 11–12% uncertainty. So
much improved.
So that's what we find. But again, this is a bit of a special case because it might be that things get a bit more complicated when you have to do direction-dependent calibration, faceting. So I think in the survey, for example, a lot of problems can come from, for example, errors in the calibration one facet that you don't really notice, but then the amplitudes are not that correct, and then suddenly the flux goes up or down. So it's a is a bit unstable in that direction. But for what concerns the instrument, I think LBA is rather good in for that. So we don't see any major systematic in the transferring the flux scale from our calibrator to the target, and the uncertainty is about indeed 10-15% this range.
Thanks. Thank you.
Okay. There's one question from Upasana Gupta. I'll read it out from the chat. So she's asking, what is smearing and subtraction when we are trying to remove noise? And how do we know how much the noise amplitude is?
The smearing problem is something that we need to keep in mind when so actually the resolution we save the data is exactly the minimum we need because of smearing with a full width of 6 degrees. So we keep a couple of you can go to 4-second time resolution, and you need a frequency resolution of about 8 channel per subband. A subband is 0.2 megahertz, so you have to do the calculation, sorry. So that's our frequency and time resolution for the smearing in our large field of view. Obviously, a bit of more problematic is when you have to subtract the very bright sources that are very, very far away, maybe 30 degrees, 40 degrees, 50 degrees, this ATM I told you. And that's why that step is done before the averaging to this level I told you. Is done usually with the 1 second resolution and 64 channel per 200 megahertz subband. So that's the highest resolution we take the data. That's used for RFI flagging, obviously, because you want high resolution, but also to remove these bright sources in the side lobes. Otherwise, you smear them and you just start increasing your noise. There's no chance then you can remove it from the longest baselines. Is this answering the question?
Yeah, I think she
Okay.
said thanks in the chat. So I was curious about the locus survey that you described. So has it already started, or when is
No.
when is the
I have a
starting one for that?
timeline, a bit of a scary timeline here. Okay, here is the timeline. So we are 24, so we are here. So this is the sun cycle. So usually you want to do low frequency observations when you are at the low part of the sun cycle. So be prepared, because 2030 is our next great moment in history. And sorry, so so we have to be prepared. But LOFAR 2, at the moment, LOFAR 1 is being phased out. So they are replacing the hardware at the stations. So we are not collecting data. 3 stations, 1 station has been already done. A couple of more stations will be done in the coming months. And the next year, the other stations will be addressed. The idea is to start collecting initial commissioning data in 2025, second half. So, maybe there will be a bit of delay, so 26. And at that point, there will be 4 years for these large programs. So 26 to 2030 is where we should collect the data for Locus and all the other large programs. Now, Locus is a proposal still at the moment. We have not anything decided yet. But is one of the large surveys that has been proposed. So hopefully, at least some part of it will be done. Clearly, being the observations at the lowest frequencies, we might have to even shift a bit ahead the observations in the last couple of years of these 4 years for the large programs, because better to observe 28, 2030 than get the data and then throw away 2/3 because of the wild ionosphere that you might still have in 26, 27. Unfortunately, yeah, with observing at tens of megahertz, you have these major problems of the ionosphere and the sun cycles. We are anyway working a lot on implementing strategies that, for example, you can use other ionospheric observables to decide, for example, whether to observe or not from begin with. So you just check the ionosphere. If the ionosphere is good, then maybe you can start doing observation at 50 megahertz. Otherwise, you do other type of observations. So this is, at the moment, was not implemented in LOFAR, but this is something that we are trying to implement in our automatic scheduling. So it kind of taking into account the ionospheric level before deciding to schedule or not ultra low frequency observations. So this maybe will improve a bit the efficiency of the ultra low frequency data, the amount of data you take.
Okay. Thank you. There's one more question in the chat. Srimoy Mitra is asking, can we go for higher than third order ionospheric corrections at the low frequencies? Can it have any significant effect?
Never checked that. I have to admit, it would be nice to have a look. It might be that, I mean, at a certain point, yes. I mean, we reached the ionospheric cutoff, which with the calm ionosphere, maybe 8 to 10 megahertz, but with the, in certain cases, it can go up to 30, 40, 50 megahertz. So in theory, you can be able to sample higher order effects. The point of noticing that there are third order effect is somewhat a kind of an alarm that it becomes very harder to do interferometry at that point. So it becomes maybe more interesting for ionospheric scientists, this type of data at that point. But yeah, I don't see why not, and would be indeed nice to check. But I have never done. I did the third order because at a certain point we couldn't see, we couldn't understand what we saw in the data, and actually the third order was enough to explain everything.
Okay, there is one more question in the chat. So Hanumant is asking, so GMRT lower band starts from 120 megahertz, which is band 2, 120 to 240 megahertz. Was there any observation done in collaboration with basically using this band?
Not really with that band, in the sense that LOFAR has also the HBA at 150 megahertz. So many observations, many times, well, if you really have to choose something, you directly choose the HBA observations, which are on average deeper. What we definitely use are surveys from GMRT, because that's our best starting model that has been used for like many years now. And as I showed, for example, for the grid, GMRT is our typical counterpart for the high frequency of the low frequency world. So there are some sources, like the grid is a very good example, that actually become barely visible at 300 megahertz. And then that's the only, really at that point, the collaboration become very, very strong, because you have, these are the only two telescopes that can really do that. Well, I think we could have used P band with the VLA, but actually we did with the GMRT directly with the lowest band of GMRT. No, I don't have in mind any specific collaboration done or type of observations done with LOFAR.
Okay, thank you. Any one last question, because we are kind of running a bit late. Any last question? Okay,
Hello.
Yeah, hi. Please ask.
Hi. Yeah. So just for my curiosity, so when you fit for the like first order, second order, third order effects of ionosphere, So basically, do you fit for that because you are not observing some calibrators or like that? Basically, using the field, you are just fitting the phases for that to get the effects.
Okay, so those images I show you where we could derive the different orders, those are done on the calibrator because we always have one beam on the calibrator. And on the target field, usually you don't have enough signal concentrated in one single direction that you can really derive those things. So we usually do a more of a brute force approach in the sense that we calibrate for some smooth phases, but we do not try to disentangle the different orders. This is something that we could do on the calibrators because there the signal to noise is high enough. So that's at the moment is the only way, the only few sources we could do it are the few calibrators I mentioned at the beginning.
Okay. Just probably a naive follow-up on that. But if we can disentangle them, and if we cannot disentangle them and just put the average corruption of the phase for the correction, how that is different? Like how does it improve the whole thing? Because we are anyway supplying that like corruption of the phase to the visibilities, right?
How the disentangling these effects is helping, you mean?
Yeah.
Yeah, no, indeed, you're right. It doesn't help in the sense that the images I show you was mostly to understand that you can describe all the systematic effects on the phases of LOFAR with just these three orders of the ionosphere and the clock, the delay in practice of the clock errors on the stations. So this was a kind of a proof of concept that everything works. And at that point, in theory, remove from the calibrator data all the ionospheric part, keep the clock and transfer the clock, because that's an instrumental systematic, direction independent. So that's one way you can exploit, let's say, the ability of separating these effects. At the moment, the software is not good enough to do that. I think only in certain case of good ionospheric conditions on. So we transfer all the phases. So in this way, we correct for the clock. We also corrupt the target for the ionosphere in the calibrator direction, which is a bit weird because you say, why you are corrupting the target with the phases on the ionosphere? But that doesn't matter too much because you are corrupting with an error that is an ionospheric 1/nu error that is 1 per station. So it's kind of summing up to any other error that you have there. So if you are able to correct the field, you are able also to correct the field corrupted by the calibrator ionosphere. But in this way, you are really getting rid of the clock, which is the instrumental part. So it goes is a bit complicated. I didn't go in all these tiny details, but you are right. In practice, you can, in theory, simply do a smooth phase, which on the target field is exactly what we do, because unfortunately we don't have any better solutions at the moment.
Yeah. Thanks.
Okay, with that, let me thank Francesco. Thank you very much for your time and
Thank you.
for the very interesting talk. We will meet again probably in the next RATeS seminar. Thank you all for attending. Thank you for your time and see you in the next edition. Thank you.
Thank you.
Bye.
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 Bye,
Have a good
everyone.
day.